Ask you a question. How many apps do you use every day? Scrolling through short videos, browsing Twitter, reading news, using ChatGPT? Behind every app, they're all doing the same thing, calling API. But do you really know how an API actually works? You click a button and the data just flies away. What actually happens in between? Why are some APIs lightning fast, while others are so slow they make you want to throw your phone? Why do so many systems crash under high concurrency? And also, why, in the A era, has the API become more important than ever? Today, let's really tear open the inside world of PI. What exactly is an API? When many people first encounter API, they feel like it's something mysterious. Let me start with the most vivid analogy. Ordering food at a restaurant. You are the customer. The waiter is the API, the kitchen is the server. The menu is the API documentation. You can't just run into the kitchen and rummage through the fridge yourself, right? You can only tell the waiter, I want a serving of braised pork. The waiter writes that request in a standard format and passes it to the kitchen. The kitchen finishes cooking and the waiter brings it to you. That's it. That whole process is one API call. In this process, the API only does three things. First, abstraction. You don't need to know if the kitchen uses a gas stove or an induction cooktop. Second, isolation. If the kitchen changes its recipe, as long as the menu stays the same, you aren't affected. Third, standardization. All customers use the same menu, no confusion. In the technical world, the most common API are HTTP API and JSON. For example, you get a user with ID 123, and the server returns that user's information. With that data, the front end can render the UI, but note API aren't just this one kind. There's also GraphQL, you get exactly the fields you ask for. There's gRPC, very fast, often used inside microservices. There are webhooks. For example, after you pay successfully, Alipay actively sends you a notification. There's WebSocket, real-time bidirectional communication, like chat or stock tickers. No matter which kind you use, the essence is the same. A mutually agreed communication rule between two programs. Looks pretty simple, right? But the really interesting part is just beginning, because one API request is far more than just sending data. What really happens when you call an API? Suppose you just click the login button. The program calls the fetch interface. What happens next? Step 1, DNS lookup. What you typed is actually a domain name. But the network doesn't recognize names, only IP addresses. So the system starts checking its records. Does the browser have a cache? No. Does the operating system have a cache? No. What about the router? Your ISP? Finally, it finds a DNS server and asks for the IP address. This step, if slow, can take tens of milliseconds. Step 2, TCP, three-way handshake. Your phone and the server go through 3 handshakes. First, phone says, I want to connect to you. Second, server says, okay, I'm ready too. Third, phone says, got it. Let's start sending data. These 3 round trips are called RTT. If network latency is 30 milliseconds, the three-way handshake takes 90 milliseconds. And if it's HTTPS, you also add a TLS handshake. Exchanging certificates and encryption keys, at least one more RTT. So HTTPS is slower than HTTP, but also more secure. Step 3, send the HTTP request. Finally, you can send data. The request message looks like this. Inside, the path, a token, cookies. The server receives it and starts parsing. Step 4, the backend truly starts working. This is the most complex step. What does it do? It needs to verify your token is correct, check the database or cache, assemble JSON. It might also call other API in between. For example, after getting user info, it finds it also needs the user's order list, so it sends another request to the order service. This is called chained invocation. One waits for another and time adds up. Where do many API get slow? It's often not the network at all. It's the database. Database I/O is hundreds of times slower than CPU. A query without an index might have to scan millions of rows. Final step. The server returns the data. The data is turned into JSON and sent back over the network. Your phone receives it, starts parsing, and updates the UI. Finally, you see the page refresh. See? A request from leaving home to coming back goes through. From DNS to TCP to TLS to send to processing to database to return to parsing. Every single step can cause delays. So, in real work, who is most often to blame for slow API? An API being slow is usually not a single cause, but many problems piling up. One of the most classic problems, too many requests. For example, some front ends open a page and need to request user info. Request avatar, request messages, request friends list, request notifications. One page load directly sending 20-something API requests. This is called a chatty API. On this kind of system, latency goes through the roof because network communication itself has a cost. Another classic problem, JSON is too big. Many API only need a username. Yet they return the user's avatar, email, address, settings, history, a whole pile of useless data. This is called overfetching. The more data transferred, the slower the serialization and parsing. And then no catching. Many people underestimate the importance of catching because databases are expensive. If every request directly hits the database, the system will soon be unable to handle the load. So many large systems check readies first. Only if the cache is missing do they go to the database. That's why catching is almost the core of modern API. In the AI era, API become even more important. Many people think that with the arrival of the AI era, backend programmers will lose their jobs. I think that statement is questionable. In fact, the opposite is true. Because AI itself is built on top of a PI. When you call ChatGPT, you are essentially calling an API. You ask it, what's the weather in New York tomorrow? Help me set an alarm. What does it do? It doesn't answer directly. It calls function calling. The model returns a JSON structure. Your code calls the real weather API. You get the result and feed it back to the model. The model says, tomorrow will be sunny and I've already set an alarm for 8 a.m. for you. See? Without a PI, AI is just a mouth that can only talk nonsense. Not to mention AI agents, an intelligent assistant helping you plan a trip. It needs to call flight, hotel, weather, map, calendar, and other API. Every step depends on API. So what is the future trend? API needs to be designed for AI. Documentation should be read not only by humans, but also by AI will automatically read your API documentation and decide for itself how to call it. This is no longer science fiction. OpenAI's plugins, Microsoft's Copilot, they are all doing this. So I say, API will become the operating system interface of the AI era. Programmers who understand API design will become more and more valuable. Many people think writing an API is just calling an interface. Too naive. What's really hard is never just writing the interface. It's security, performance, scalability, compatibility. For example, security, does your API need authentication? Use a PI key, JWT? OAuth. How do you prevent someone from forging requests? How do you prevent replay attacks? Rate limiting. Someone sends 10,000 requests per second. You can't let them blow up your service, right? Use the token bucket algorithm. Exceed the limit. Return HTTP 429. Idempotency. A payment endpoint. The user accidentally clicks twice. Can you guarantee the money is deducted only once? The client sends an idempotency key and the server records it. Pagination. Your user list has 100,000 entries. Are you going to return them all at once? Not possible. You have to use limit and offset or cursor-based pagination, which performs better. Versioning. Once an API is published, you can't change it arbitrarily. What about incompatible changes? Add v2 in the URL. Error responses. Don't return random strings. Standardize them with HTTP status codes. Documentation. An API without documentation is not an API. Use Swagger to generate it automatically. Testable online. Observability. Every API needs latency and error rate monitoring. If P99 latency exceeds 200 milliseconds, you need an alert. Also, a trace ID, stringing together the entire call chain for each request to make troubleshooting easier. So you see, writing an API that works is very simple. Writing an API that remains pleasant to maintain 10 years later is extremely difficult.